So, okay, I will see yesterday last thing become a bit messy. So, I will start recalling the definition of Chevalier group. Okay. So, L, H and pi root system associated with this and delta base, these things are there, and U, L, Z for the constant lattice notation we have used, and M is inadmissible lattice. So, V is a faithful, this is a faithful L model. Okay. So, now and take M to be admissible lattice. So, this is a finite dimensional model. So, then we have associated a group which we have called Chevalier group. So, you fix a basis of this M, Z basis of this. So, let this M1, M2 and MD, this is a basis, this is a Z basis of M, okay, and T is an indeterminate. So, this is an indeterminate. And of course, the Chevalier basis is also fixed. Okay. So, our Chevalier basis is H I and X alpha etc. Alpha and phi. This is also fixed. This was. Okay. So, then we have added notation, and suppose rho is representation afforded by this model this, then we have defined, we have agreed for the notation this rho n, and so T n tensor rho x alpha or n by this factorial n to be just T n rho x alpha by factorial n or n. So, now you consider this model M. So, this Z T tensor M over Z. Okay. So, you consider this model. So, then here it has a basis. So, this is Z T module, and it has a basis one tensor M1 etc. and MD tensor. So, one tensor MD, right. So, this is Z T basis of this model Z T tensor M, right. So, now okay. So, write down the matrix of this representation. Suppose suppose this E L for T. So, E L for T, this is the matrix of this transformation exponential rho. So, this is a T rho x alpha. So, with respect to the, if I call this with respect to this basis, let us call say B. So, you consider the this matrix with respect to B. So, now see the entry of this, what is the entry of this matrix? So, since how this transformation is going to act, if you remember, so this exponential t rho x alpha is 1 plus t rho x alpha. So, this t means t tensor. So, this is a t tensor rho x alpha plus t square rho x alpha square upon factorial 2 and so on, and since it is nilpotent, so it is going to 0 after a certain stage. Okay. So, if I take effect of this transformation say at M1 at this element, then what will happen at this element? So, since this is admissible lattice, so this kind of transformation at rho x alpha I by factorial I. Okay. So, this takes M inside M, this will take M inside M because this is a definition. So, if I take the effect of this transformation at M1, then this will you get M1 here plus T tensor this of M1, which is an integral combination of the basis, and T square rho x alpha upon factorial 2. If I take the effect of this at M1, again it will be integral linear combination, right. So, this transformation acted at M1 is integral combination of MI's. Similarly, any if you take anything here, so that will be integral combination here. So, the matrix here, the coefficient of the matrix E alpha t are precisely in Z t, right. So, okay. Now, since rho x alpha say by any power say I factorial I of M is inside M. So, therefore, so entries of E alpha t is inside Z t, right. Is inside Z t. Further, this is okay. No, entry of the matrix. Entries of the matrix. Okay. So, this is inside, and this will of course invertible matrix. And further, if so, further, if t and t prime are indeterminate, both indeterminate, then exponential t plus t prime rho x alpha. Okay. So, this is exponential t rho x alpha into exponential t prime rho x alpha. Am I right? Because these two matrices they commute. So, therefore, exponential the exponential will be the product of the exponential. Okay. So, now these two things, so since the entry is going to be a polynomial in T with integral coefficient, so therefore, the this indeterminate can be specialized to element of the field to give an entry inside field. Okay. So, therefore, so thus if K is any field, then what you have E alpha u, and if you suppose u inside K, then so this the matrix inside where GLD K. Am I right? Because this is the so this matrix. So, this is a D cross D matrix, invertible matrix over entry in polynomial with integer coefficient. So, if I specialize T, by element of the field, then I can get invertible matrix D cross D matrix with coefficient in field. Okay. And further what you have, and we have E alpha u plus u prime is E alpha u into E alpha u prime for every u and u prime belongs to K. Because of this this thing. So, now the notation now for u inside K, u inside K. So, this is the x alpha u and alpha belongs to phi. X alpha u is the automorphism of we have written V k, which is K tensor M, okay, defined by the matrix E alpha u with respect to basis, which basis? One tensor M1 etc., one tensor MD. So, this is an invertible matrix with coefficient in K and D cross T. So, this will define a linear transformation, okay, invertible linear transformation, and that is of this thing. Okay. So, now G V K is the group of such linear transformation. So, this is a group of linear transformation x alpha u, where alpha belongs to phi and u belongs to K. So, this is a subgroup of what? GL VK, right? GL VK. So, this is called Chevalier group. Chevalier group. Over K associated to V, and we will observe later that this depends only on the certain lattice of this field. Okay. So, if V is if rho is add, then G V K is called adjoint Chevalier group of adjoint type. Adjoint type. In fact, okay, and if the lattice, if the inversal lattice, then it is called inversal type. So, if rho v is inversal lattice, that means the lattice generated by all fundamental dominant weight, okay. Then G is called GV is called inversal Chevalier group. Chevalier group over K. Of course, of type L. So, now I will take some examples, then things will become a bit clear. So, let us take the Where? Yeah, L is there, na? L तो पहले से ही है. L has been fixed here. Yeah, I should write several notations because G, V, K, M, several things. So, and base, wale base, so many things. But I am dropping because so many things has to be dropped at later stage. So, I am okay. So, this is a Shivale group. Actually, it depends on the lattice and not on the representation you are taking. So, because many representation is going to give root lattice, many representation are going to give universal lattice, and Shivale group is same for such thing. So, it is a group defined dependent only on the field and lattice, SLN plus 1, right. Now, take M. So, then we know that so what is H? H I can take the diagonal lambda 1, lambda 2, lambda n plus 1. So, such that this all lambda I belongs to K, and K is a field and K field, and some lambda I is 0. Okay. And Eij, this denote the matrix, you know at, so this is the matrix. So, ijth entry is 1, this is jth, and this is the ith position. So, ijth entry is 1 and all other entries are 0. So, this is the Eij, this matrix. Then L has decomposition, what decomposition? H tensor, direct sum of C E I J, right. So, now we have given exercise yesterday that find Shivale basis of this Lie algebra, and you might have seen that H I, if I take H I equal to E I minus E I plus 1, so that I 1 less than I less than equal to n union E I j, so that 1 less than equal to I different from j, all this, and less than equal to n plus 1. So, this is a Shivale basis. Right. So, I have seen that this is Shivale basis, and now take your lattice M to be lattice M. So, call this basis to be B. So, M is Z span of B, which you have written LZ, right. L span of Shivale basis, we have given certain name LZ. So, look at this, and suppose our representation is add representation, then what are our transformation, what is the matrix E alpha u and X alpha, transformation X alpha u. So, first you notice the following, that for a Eij, so just you note Eij square is 0 if I different from j, right. If I apply double, then becomes 0. So, and second thing is, if I take any element, say suppose I take T to be any element or use any element of the field K, then so exponential u okay, and any such element, say any element, say e I j exponential u e I j. So, because e I j is nilpotent, and take any matrix, say matrix A inside L, this is A inside L, then what it is going to do? So, it is exactly going to do. So, this is exponential so apply, say add of say e I j and applied this transformation at A. So, first of all, what is the matrix E alpha? Okay, so I am sorry. So, what is the matrix say E, what are the roots? Roots are alpha I j, alpha I j are the roots. Okay. So, if I take E alpha I j, so what are these alpha I j roots? So, this and diagonal elements lambda 1, lambda 2, lambda n to lambda I minus lambda j. So, this there. So, this of u, so remember, so this is the matrix. What is the matrix this? This is the precisely the matrix so I say that this is the matrix whose ijth position is 0 and rest position is 0. Okay. So, this is the identity plus Eij matrix, u times Eij matrix. Why? Because if you remember, so the definition of this, so Ei, how to get the matrix of this with respect to add representation. So, this I think I have rubbed it here. So, E alpha u, this is the matrix which is obtained of exponent, what is the matrix? Of the exponential u rho x alpha. Okay. So, this is the matrix. So, in fact, this is the matrix of the matrix of exponential u e I j, which is nothing but identity plus e I j, u times e I j. Why? Because you know that e I j square is 0. So, this is the identity plus u times e I j plus u square e I j square 1 factorial 2, that is going to be 0. So, therefore, this is going to be this matrix. Okay. And what is the transformation associated with this? So, x e I j, so x alpha, so this is so x alpha I j u is the transformation associated with this matrix, right? What is this? So, this is transformation exactly exponential. If you remember, so you add e I j. So, x alpha u is the transformation automorphism associated with this matrix, right. So, this is a transformation of what? This is a transformation of LZ tensor K. So, so this is we have LZ tensor K, this is space, suppose I call it Vk. So, the transformation which is associated with this matrix is this one, x alpha is alpha I j, x alpha u, which is exactly this transformation. Okay. So, u and suppose representation is adjoint, I am sorry. So, for the add representation. So, rho is also rho to be add representation. So, therefore, this is going to be what? So, if I take, if you remember exercise study we have given, if you have any nilpotent derivations, this is nilpotent matrix. So, then this is a precisely if I act at certain element. So, for example, so therefore, if A is any matrix where inside SL n plus 1 K. So, where is this matrix? This matrix is SL, I am sorry. So, this matrix is SL n plus 1 K. If any is any matrix SL n plus 1 K, then so this transformation x alpha I j of u will take A to where? Exponential u e I j A and exponential u e I j inverse, right. This exercise given yesterday or today. So, this since this is nilpotent, this is nilpotent, and so therefore, u times this is precisely this matrix. So, therefore, we have a correspondence with this. So, it takes A to this transformation. Now, suppose say G tilde. So, this is the group. So, what is the subgroup generated by such kind of matrix? So, this is the matrix which is identity in the one in the diagonal and ijth position is u, such matrices generates. Okay. So, now since so this is an exercise now, since the matrix of the kind I place u a I j where u u in K and I differ from J generates SL n plus 1 K, and it satisfied, for example, the plus thing. Therefore, we have hence we have this we have a homomorphism, say phi say theta from S L n plus 1 K to the Shivale group, which is a G V. What is a V? V is L, G V K. V is L and rho is our adjoint representation. Okay. So, what is the homomorphism? Theta of A simply goes to theta A. So, A goes to the transformation theta A, and theta is what it does? It takes entry by just conjugation. Okay. So, for example, so A goes to conjugation. So, A goes to conjugation by A. So, this is the A goes to the conjugation by A. By A. So, A goes to conjugation by A, right. So, therefore, what is the kernel of this? Kernel will precisely those matrices which commute with this. Okay. Therefore, that will be the scalar matrices. So, therefore, kernel of theta is the center. Kernel of theta is precisely the center of S L n plus 1 K. And this is onto because X, the element of the kind X alpha I Z U, they generate or Chevalier groups, and this okay. Which one? Image is here. No, see here. Look at the argument here. X alpha I J U. Okay. So this is a transformation associated with this elementary matrix, elementary non-singular matrix. So you have a correspondence. A goes to and what is this transformation? This transformation is simply conjugation by this element U E I J. This is the conjugation by U E I J. So therefore, so what you have a map. So therefore, you have a natural map from, and such kind of matrices is there, they generate SLN plus K. So therefore, you have a map from SLN plus K to this, which takes a element. Okay, 8 goes to the map conjugation by A. Conjugation of what? Conjugation of this SLN plus K.
So if I can repeat, E alpha I J will give this matrix, and X alpha I J U is by definition the automorphism.
Automorphism, I am sorry, VK.
Given by this matrix.
Yes.
And we observe that the automorphism just makes conjugation. So here this A is really that exponential U E I J.
That's true, but see, so this is true for the generator wise this is true, and since they are going to generate, so in general the map is A goes to the conjugation by A. Is okay? Okay, so this kind of element, this kind of matrices, they generate SLN plus K, and from each level we have a map which is a conjugation by exactly that element. Since those elements generate this, therefore we have homomorphism from here to here. So and kernel is what? Kernel is precisely the center of this. So therefore, Chevalier group of adjoint type is precisely the SLN by its center. See, if you are not sure, then please write decrease n, make it n equal to 1 or n equal to 2, because then there are not many roots, just one positive root, okay, and things. So therefore, in this case G V K is isomorphic to what is called P S L n plus 1 K. See, the same is true.
I have one more observation. This A should really be in the Lie algebra because it's acting on the representation space. It should not be.
Yeah. This is on the Lie algebra, right? Because this is a Lie algebra automorphism. Actually, this is inside S L n plus 1 K, which is our V K. Please make correction. So the V K is this vector space, and in this vector space it is it is automorphism of that vector space. In fact, this is in fact Lie algebra, and it is in fact Lie algebra automorphism. So therefore, this is going to be exactly this. Now take another example. The same Lie algebra. L is again the same thing. Say let us take SL2, but the same is true for SLN, and rho is the standard representation. So V is your C2. Okay. So then in this case, you know that mz E1 plus z E2. So where E1 E2 is standard unit vector. So that is E1 is 1 0, E2 is 0 1. So study, you have seen that this is a lattice. This is a lattice, admissible lattice, right? This is admissible lattice. So, in this case, what is the and V is our K tensor M, Vk is K tensor M. What is the action? So, this is nothing but K2, K square. Okay. So, what is the action of this Lie algebra there? So, because you have to simply compute the transformation. So, rho is our standard. So, exponential, what is the exponential? Say u rho, there is, so E12 and E21 there. Okay. So, rho, say E1 Eij. So, if I take any vector here, so what are the basis vector here? Basis vector are again 1 0 1 comma 0 and 0 comma 1. Okay. So, what is the, first of all, what is the matrix it is going to represent? So, the matrix it is going to represent is 1 plus u times rho is the standard representation. So, this is the u times Eij. So, this is either matrix. So, this is the and Eij square is 0. So, this is the matrix either 1 1 u or 1 1 u here, this kind of matrix there. Okay. And how it acts on a vector space? So, this transformation, so the so namely x alpha u is the transformation associated with the matrix. So, so this is either 1 0 1 u or 1 u 0 1, right, this kind of matrix. So, this at E1, that means at 1 0 1 comma 0 which is E1, how it acts? It is precisely, so this let us call it say again E1. So, this is a E1 plus so let us put, so alpha is, what are the roots here? So, x alpha is alpha 1 2, alpha is alpha 1 2. So, what it is? See, these notations are a bit, so x alpha, alpha stands for the, see these are the vector, they are not roots, they are x alpha, not alpha. X alpha, alpha is root and these are the x alphas. Okay. So, at this point, so what is the, so this is what it is? This is exactly, I say, identity plus u times u times this matrix E, so E, so this E11, okay, because you have a standard representation. So, identity plus u times E11, E12, and similarly x alpha 2 1.
We are just taking the image of the first column. Only the first column will come. Only
E1, right. So, I have taken, okay, so let us write like this. So, this will be, okay, so this will be E1 plus u times E12 of E1, right. So, which is E1 plus u times E2.
E12 is now 0 except at the 1 2 place.
So, 1 2, so E2 goes to E1.
But E1 goes to
Right, E1 goes to 0. So, this okay. So, this is 0 and x alpha 1 to u of E2 means 0 comma 1. So, what it is? So, this is E2 plus u times E12 matrix of E2, which is E2 plus u times E1. Okay. So, therefore, it represents the transformation so therefore, this x alpha 1 to u represents the transformation, the automorphism which automorphism? In the matrix form writing. So, automorphism it takes E1 to E1. Okay. So, that means 1 comma 0 and it takes it takes E2 to E2 plus u times E1. Okay. So, this is u, this is 1 here. So, the transformation is exactly associated with this. Similarly, okay. So, the transformation associated with this and similarly we have x 2 1 alpha 2 1 of u is associated to which 1 u 0 1. So, therefore, in this case the Chevalier group is precisely E12 is the first row and second column 1 and all others 0. EIJ matrices. Yes. So, therefore, in this case what is the Chevalier group? So, thus in this case Chevalier group is isomorphic to what? The subgroup generated by the matrices of the form 1 u 0 1 and 1 u 0 1 where u belongs to K, and it is exercised that this is isomorphic to SL2. Yes. This is exercise, this is SL2. So, which one? That will come automatically. That is exercise. Okay. This is exercise. Whatever you are burying, that will come, but as an exercise. So, therefore, we have constructed both Chevalier group, because if you have done exercises, there are only 2 lattices for SL2 and for 1, and therefore, there will be only 2 groups, and we have constructed both. One is SL2, another is PSL2. Okay, SL2 modular is centered. So, both groups have been constructed here. And similarly, if I take the SLN Lie algebra kind AN and standard representation, you will get the standard this universal Chevalier group corresponding to the standard representation. The same lattice generated by all EIs. Okay. So, I hope you have got some idea of the Chevalier group. at least some example. Now, we will notice some properties of Chevalier group. By the way, the references which I am using is of course Humphreys, and Carter's, okay, Carter's book on finite, Carter's book, simple groups of Lie type, Carter, ne? CRTER, TER. So, the title says the simple groups of Lie type, simple groups of Lie type, simple groups of Lie type, okay. And there is a very good lecture notes of Sternberg's, lecture note. I think this is available in many places, and you can ask if you want our friend have copy of, at least they have soft copy of the note. So, you will get the soft copy, Sternberg lecture notes, and this, and there is an article of Curtis, very concise article of Curtis, which says the Chevalier groups and related topics. Okay. So, you will get the references there. So, these are the main references which I have used. Okay. Now, let us move for some properties of Chevalier groups. You will see that Chevalier groups enjoy very interesting properties. See, adjoint of Chevalier groups is some kind of smallest Chevalier group, and universal type is the largest one, and all others are in between, okay, between adjoint and universal. So, what is known as Chevalier commutator formula. So, this is I will not prove the theorem, but I will just state it. So, this is a Chevalier commutator formula. So, L etcetera everything is there. Suppose alpha, beta and alpha plus beta are their roots there. Okay. So, then and say T and suppose T and U are indeterminate, minutes. So, then there exist unique the exist integers Cij, integers Cij such that, so what you have such that exponential T you consider T x alpha and okay, that is x, and exponential T x beta. So, you take one place at T and other place at U, U x beta is product of the following element: exponential Ti Uj Cij, Ti Uj, and then x I alpha plus j beta, and okay. So, this where this belongs, this element belongs to the formal power series ring of UL TU. Okay. This symbol belongs to formal power series, and where the product runs, the product run over some ordering of the roots so the product runs over some ordering, some ordering, whatever ordering you take, fix it, fix an order of roots of type I alpha plus j beta, I j both greater than or equal to 1, starting from alpha plus beta. So, the first element is that means C11, okay. The first element in the ordering is alpha plus beta is a root. So, first element in the ordering is alpha plus beta, and you fix some other ordering, and then Cij only depend on the ordering. Cij depends only on the ordering. On the ordering of roots alpha plus j beta, okay. And further C11 is n alpha beta. You remember n alpha beta? N alpha beta is what? Plus minus r plus 1, okay. So C11 is the first one integer is precisely this. So now this formula is over in the formal power series ring. I can specialize it the indeterminate T and U to element of any field to get a Chevalier commutator formula over this, okay. So therefore, this is the advantage of getting something over indeterminate, that you can always specialize over this. So therefore, thus if K is any field and G is your GVK is a Chevalier group, then in the above theorem T and U can be specialized to element of, then we can specialize T and U to be elements of K to get a commutator formula. Right. In G. So that means the commutator formula hold for any Chevalier group. So this is the general statement, and this integer also depend on the ordering of this. The first one is n alpha beta and so on. So you see many things will be dependent only on certain kind of thing and not, okay. So not on the representation and so on. This is a formal power series ring. This is inversely enveloping algebra, okay, because these are the elements there. So for example, if suppose alpha plus beta is only root, then there will be only one term, right? And if alpha plus beta is only root, so there, then you have simply n alpha beta here and Tu, and suppose all roots have same length. You have done exercise. All roots have same length, then n alpha beta is plus minus 1. So, for example, in type A n, D n, R a, E n. Okay. So, you have all roots have same length. So, therefore, you have plus minus times T u. This is special case there.
So for the cases, can one just rank two root systems to find this Cij?
One can get, of course, Cij, but case wise one has to
B2, G2.
B2, G2.
But that will be enough then.
Huh?
That will be enough to do even other cases.
Yeah, because this is the rank 2 thing. This involves only rank 2 root system. So, it is enough to do further. I think Carter has done. Carter has determined the up to may be sign.
So it will also tell the order.
Up to sign. Then see ordering. Ordering is yours. Okay. But the first element is alpha plus beta. So, but if you change the order, then this Cij will get changed.
But only for G2 there will be a problem. Otherwise, for B2 there is a natural order. Alpha plus beta, alpha plus 2 beta.
Yeah. So, every root system has natural order because the positive roots can be ordered in terms of height. So, but anyway, see this the kind of root I alpha plus j beta are there. So you take all of them and start with alpha plus beta and give some order. Then this integer will be determined completely. They will depend on the ordering only. So that means whatever representation you take, this is going to be there, right? But depending on the characteristic, you see if you specialize T u to be element of the field, then this integer will be inside the will be the prime. This will be represent some prime in the prime field. So there some might be 0. For example, even characteristic 2, if some Cij is 2, then it is 0. Nice situation. Okay. Okay, let us quickly do something, some basic thing. Now I will just write the G is just Chevalier group. Now G is a Chevalier group. Okay, and you define U to be. So this is a definition now. U to be the subgroup. Okay, so maybe at first. So you define X alpha. Definition is the subgroup generated by all element of the form X alpha U. U belongs to your field K over some field K. So is belongs to K and some representation. Okay, and now U to be the subgroup generated by X alpha positive root. Then you have following thing. You define Ui to be the subgroup generated by X alpha, so that height of alpha is greater than or equal to I. So alpha positive root. So alpha is a positive root. So you take okay, this is called the root subgroup. Root subgroup of G, a root subgroup of G, and U is the subgroup generated by all root subgroup for positive, and Ui is generated by those root subgroup whose height is greater than or equal to I. Okay. So, these are this. So, then we have a central series, then proposition is the following. So, then first thing is, first property is let me write proposition. So, you have a central series U, which is U1 contained in U2 is a central series, and second thing is, so U consists of unipotent endomorphism on Vk. What is V? And V is over K and a representation V of L. So, this has central series 1, and the second statement says that U consists of unipotent endomorphisms. On Vk, right? Vk, you understand, Vk means you have taken a lattice inside M and tensed with K. And then each, the third statement says that each x, if each x in U has unique representation, representation as x is product of x alpha u, x alpha say t alpha, okay, and alpha is alpha in positive root, and the product is taken in the increasing order of, okay. The product is taken over increasing order of roots. That is in terms of height. So, then there is one more statement that if I take, so fixed element W belongs to W. So, this is the while group of L, that is of phi. Then and you defined U W plus this is the subgroup generated by those x alpha, so that alpha is positive and W alpha is also positive, right, and U W minus. So, this is the subgroup generated by those x alpha is positive, but W alpha is negative. Then U is U W plus into U W minus, and U W plus intersection U W minus is trivial. Okay. So, the proof is commutator formula in fact. The proof requires a commutator formula. If you remember, so look at the commutator formula here. So, look at the right hand side. So, I, j are they are both greater than or equal to 1, right. So, if alpha has height say k and beta has height j, then the roots on this side has height k plus l, greater than or equal to k plus l, right. So, therefore, if I take or just so if I take say u I and say u j and this and take the commutator and apply the commutator formula. So, then this is going to be contained inside where u I plus j, right. See, look at here. So, if I have certain height, it has certain height. So, suppose it has height k, it has height l, then height on the right hand side is greater than or equal to k plus l, k plus l. So, here the elements are the elements, this is a subgroup generated by the root subgroup of height greater than or equal to I, and subgroup generated by height greater than or equal to j. So, if I take the commutator subgroup by this, then the so then it will be contained inside here, height will be greater than or equal to I plus j. So, in particular if I take u I and u then this is going to be contained in u I plus 1. So, then what it says? It says that the element. So, what it says? That you consider this subgroup quotient group u by u I plus 1 and consider this subgroup u I by u I plus 1. So, this is a So, this is contained in the center of this. Why? Because if I take element here and I take element here, then its commutator fall inside here. So this implies that this is contained in the center of this subgroup. And also why it is, so I should have said why it is normal. It also follows from the commutator formula that if you take conjugate of any element here by any element here, then you will get height to be greater than I. So, therefore, it is contained in I. So, these are normal subgroups of U and they are contained in the center of this. U I by U I plus 1 is contained in the center of this. So, therefore, it is a central series. It is central series, and since height is there is finite height, and therefore, at one stage the subgroup U I is going to be trivial. So, therefore, the group is nilpotent, right. So, this is the argument. If I write it, it will take some time, but you can take it and write down the proof, the argument which I have told. Apply commutator formula to show that first this is a normal here and this is contained in the center of this. So, this is one. And why it is consist of unipotent? Unipotent means what? Identity plus nilpotent. So, for 2 you just what you do? You decompose for the proof of 2. you write V as direct sum of its bit spaces V. So, Vk is Vk mu and mu in the weights of representation, right, the weight of the representation. So, you consider a basis. So, let let B mu, where mu belongs to PV. This is a basis of Vk mu and give some ordering, okay, and give some ordering and take the basis B. So, this basis B is union of all, let me write, B is union of this B mu in PV. So, what you do, you get a basis of this consisting of basis vector from eigen subspaces, okay, and you take a basis from eigen subspaces and give arbitrary order of inside the eigenspace, and then the ordering here you give like this. So, ordered B in the following way. Suppose an element here, so suppose some element, say some element V inside B mu B, okay, mu precedes to some element W inside, say B mu prime, if so, if mu is less than mu prime, strictly less than mu prime. So, this is in the ordering of the weight, that is mu prime minus mu is a sum of positive root. Okay. So, what I am saying that, so you or B is like this. So, you have taken a basis of B mu, okay, suppose this is a contribution from mu, and if mu is coming, mu is less than, say, mu prime, then the elements of mu prime are after mu, okay, and so on. So, you start with the basis and this arrange the roots in the increasing order, in the natural order of the weight. This is the ordering of the weight. This weight is less than this if the sum of positive roots, the strict inequality, and you okay. So, then you arrange basis like this. Then, if you write down the elements of U with respect to this basis, then it is a lower triangular matrix, right. Then each x in U represents a lower triangular matrix, triangular, matrix with respect to B. Am I right? So, because you have obtained a basis consisting from these eigen subspaces and given the ordering like this, then if you want to write down the matrix of the endomorphism T, then it will be lower triangular matrix. So, therefore, it is unipotent. This is done, okay. And 345, right? And why this is a unique expression? For the proof of 3, you fix some element, say suppose x belongs to u and alpha is some positive root. So, since the representation is faithful, so since V is faithful, then there exists some mu in PV and some vector V inside Vk mu such that what says that x alpha dot V is non-zero, right? Because every positive this basis element cannot kill. Why? Because the representation is faithful, because V is faithful. V is faithful. L model. So, for the Chevalier group, we take a faithful representation. So, therefore, certainly you can get like this. And if so, first of all, you consider the see every element, whatever element of you will take, that will be certainly a product like this, not in this order, but in whatever order. So, it will be product of this element because it is generated by root subgroup. Okay. So, you consider x alpha t. So, you can consider x alpha t. So, exponential, that means x alpha t. So, t belongs to some k. And so, what is x alpha t? So, this is your exponential t, if the rho is the associated representation of x alpha. So, this is a 1 plus t times and if I apply at element V, so this has V and t rho x alpha V plus some other element, and this is okay, and here you will get V. So, you get V plus t times, so where it will go? So, this is x alpha V, but this and some element y. So, where this belongs? This element, this belongs to the sum of V k mu prime, where mu is inside PV, but mu is different, mu prime is different from mu and alpha, because V is in the alpha eigenspace, V is in the mu eigen subspace, and if you act by x alpha, it will go inside mu plus alpha, right. So, this is a mu and mu plus alpha, mu and mu plus alpha. So, this is so it will be this will be the this will split as sum of element in the eigen subspaces. So, this is a component from B mu and this is a component from this is a component where from V mu plus alpha, okay. And right is y is sum of all other element, the sum of all other element, okay. So, suppose you have two different representation of x, okay. Suppose you have two different, suppose your x has written in two different ways. That what does it mean? That means coefficient of x alpha is T1 and T2, etc., etc. So, in one of these things you will get V plus T times x alpha V, and in the other expression we will get V plus some T2 times x alpha into V. Okay, I do not care about the other thing, but since these are the vectors from distinct eigen subspaces, therefore, they will be linearly independent. Okay. So, you are done. Should I repeat it? See, what I am saying that this is non-zero vector, right? V is non-zero vector. Of course, it is non-zero vector because of this condition. So, it is non-zero vector. So, and this is another eigenspace. So, this element and this element, they fall in different eigen subspaces. So, therefore, they are linearly independent. So, if I suppose in the expression of x alpha, so there are two things. Okay. So, in the expression of x alpha, you have two different expression. What does it mean? That means you get coefficient T alpha and T alpha prime. So, on one hand you will get the coefficient T alpha here, and another thing will get expression T alpha prime, but since they are linearly independent, so this cannot be possible. So, therefore, T alpha must be unique, and of course, this product you can write increasing order by applying Chevalier commutator formula. Okay. The product can be written in the increasing order of the in terms of height because of Chevalier commutator formula, and the uniqueness follows from this argument. Okay. So, I will give an exercise. See, if we take the fourth one, so u w plus intersection u w minus this is of course trivial, right? This is okay. So, this is by 3 because okay. So, the roots which are appearing here and here, they are disjoint. For one w making positive, other w making negative. So, and you know that every element has unique expression like this. So, once a root is there, okay. So, once you have some alpha is there, it cannot be some different alpha in the expression. So, therefore, this intersection is unique, and why this will be u equal to u w plus into u w minus. So, this exercise you just apply induction on the this you think of, you try to just prove that first u I is u I plus into u w I plus, and first you take the ith component, okay, and then u w minus I. So, for example, I barabar 1 is this case. So, apply the induction from bottom, opposite direction. So, this is exercise to you. Okay. See, the uniqueness also say that suppose a field has k element, then this subgroup has order q power n, right, because of this finiteness and so on. So, there are several remarks, and so let us define some 2-3 minutes are there. So, define some new elements. So, definition is G is of course our Chevalier group, and phi is root. You define W alpha T, alpha is root, and T is element of or field K. You define what is called W alpha T to element X alpha T. So, this is a definition, X alpha T, x minus alpha minus T inverse and x alpha T. And H alpha T is in K star. X alpha T. T or T inverse? T, ne? I think T. Otherwise, I will correct tomorrow. Tomorrow, I think it is T. And H alpha T is W alpha T and W alpha minus 1. Okay. So, you call subgroup generated by this sorry, which one? H alpha T is W alpha T, I am sorry, W alpha T and W alpha minus 1. Okay. So, N is a subgroup generated by W alpha T. Okay, maybe I should not first define this. So, you call H with the subgroup generated by H, all H alpha T, so the alpha in phi and T in K star. So, there is some very interesting property, maybe I will just mention them next time and mention some important property, and then you see that if I take the subgroup generated by this kind of element, then H is normal there and the quotient group is Weyl group. Okay. So, every Shewaley group is going to contain a copy of your Weyl group, and the theory says that the group can be reconstructed from those things. Weyl group is starting. So, starting from the root system itself, you get everything, Lie algebra, Shewaley group, okay, because Weyl group is there in hand. So, you need only root system and field, and then you should be able to construct everything. So, I will may not be able to do many things, but I will list certain property. And last lecture, I will try to prove that, at least give a sketch of the proof that if you take K to be finite field or K to be any field, but not very small field. For example, K is not 2 in certain cases, K is not of order 3, only very few exceptions, just 2 or 3. So, then all adjoint of groups are simple. So, this is a Shewaley theorem, Shewaley-Dixon theorem. So, this is going to be a very major part of the finite simple group, okay, adjoint type. And there is some other thing, some other groups of Lie type, they are the twisted version of this, but I do not think I should be able to go there. But at least this simplicity of adjoint type, I will try to indicate next time. Okay, thank you.